In this video, we will learn about half-lives and doing calculation regarding half-lives. So for these radioactive elements, they are decaying. And so a half-life is how much time it takes for half of the parent nuclide to decay into the daughter nuclide. So it can be abbreviated either T with a subscript 1/2 or H. You'll see it both ways, T 1/2 or H. But it's about how much time it takes for half of the substance to disappear. So in this graph, you can see that initially you start off with 20 milligrams of iodine 131. When one half-life has happened, you have half that much, which is 10. Then 1/2 of 10 is 5. And so that's a second half-life is when you reach 5. And then half of 5 is 2.5. And so that takes 3 half-lives to reach 2.5 milligrams. And then you would take a fourth half-life to reach half of that. And then a fifth half-life to reach half of that. And so a half-life is how much time it takes. So it takes 8 days for half of go from 20 to 10. And it takes an additional 8 days to go from 10 to 5. This time so that length of the half-life can be used to calculate how old an object is. In Chem 3A, we're going to be focusing on calculating whole numbers of half-lives. This is a handy equation to calculate, but we'll also be covering a more conceptual way of mapping out how much is left or how much time has occurred. But in this way, we're going to take our initial amount and multiply by 1/2 raised to an exponent to figure out how much time has elapsed. So total time over how long a half-life is. That will tell us how many half-lives have occurred. And that will give us our final amount. Each different radioactive isotope will have a different half-life. And so, for example, carbon-14 has a half-life of 5,730 years. So carbon-14 will take a very long time to complete one half-life. But all these other naturally occurring isotopes also have rather long half-lives. For medical applications, they want to use something with a much shorter half-life, something that can actually decay in a human's lifetime. And so all the medical isotopes have much shorter half-lives compared to the naturally occurring isotopes. Here's a practice problem for us to work on regarding half-lives. It says iodine 131 is used to measure activity in the thyroid gland. If 88 milligrams of iodine 131 are ingested, so that's my initial amount, how much remains after 24 days? And so that's my total time. And then it tells me my half-life. And so my first method, I'm going to map this out more conceptually. And so I start initially with 88 milligrams. After one half-life is 8 days. And so I'm going to write total days down here. My total days is 8 days so far. After 8 days, I'm going to have half of that. And so that's going to be 44 milligrams. After an additional half-life, I'll be up to 16 days. And so I'll have half of 44, which is 22 milligrams. That's my second half-life. It's 8 more days. Now, after a third half-life, after another 8 days, I'm going to be up to the 24 days that the problem asked for. And so after this, I'm going to stop and figure out what this is. And so that's 11 milligrams. And so I will have 11 milligrams left after 24 days. Another way of figuring this out is looking at how many half-lives have occurred. And so my total time is 24 days, and each half-life takes 8 days. And so that means that I'm going to have 3 half-lives. And so then I can take my initial amount of 88 milligrams and multiply by 1/2 3 times. And so I can simplify that to 88 milligrams times 1/2 to the third power. And that is also equal to 11 milligrams left. This method is similar to that equation that was on the previous slide, where we had our initial amount times 1/2 raised to the exponent of total time over the half-life time gives us our final amount. Okay, let's do a practice problem. Go ahead and pause the video and work out this problem. It reads, the amount of carbon-14 in a living organism is constant until death of that organism. The amount of carbon-14 in a specimen can be used to calculate how long ago the organism died. The half-life of carbon-14 is 5,730 years. If a living specimen has 0.512 milligrams of carbon-14, how old is a specimen that contains 0.00800 milligrams? Pause the video and work that out. Okay, let's work this out. So this is my initial amount. This is my half-life. And this is my final amount. I'm going to use the conceptual mapping method of working this out. Although if you are confident in algebra, you can also use that equation that I gave you. But our initial amount is 512 milligrams. And then after 1 half-life, I'm going to have half of that. And so that is 0.512 times 1/2. And so that would be 0.256 milligrams. After a second half-life, I'd have half of that. And so that would be 0.128 milligrams. And then I'll stop once I see the 0.080 number. And then again, multiply by 1/2 until we see that final amount. and then multiply by 0 1/2 again. Still haven't reached that final amount yet. Keep multiplying by 1/2 until you see, aha, that's my final amount. Okay, so that's my initial amount. And so now we have to count how many half-lives have occurred. I've done 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives, 6 half-lives. 6 half-lives. 6 half-lives. And so each half-life is 5,730 years. And so 6 times 5,730 is 34,380 years. Okay. If you want additional practice problems on that, there are additional practice problems on the worksheet for chapter 17/16.